Let me just do a little introduction here. Welcome to the SO-CHIC webinar for Work Package 5. My name is Griffith Kauser. I'm a policy officer at the European Polar Board, which is a membership-based organization representing polar programs of 29 different national research agencies, universities, and funding agencies. And just so everyone is absolutely clear, this webinar is being recorded and will be available on the SO-CHIC YouTube channel in the near future. SO-CHIC is an EU-funded Horizon 2020 project focused on measuring and understanding heat and carbon exchanges between the atmosphere and the Southern Ocean. SO-CHIC aims to add valuable data and understanding to the heat exchanges in the Southern Ocean. Began in August 2018 and comprises of 18 different institutions. The European Polar Board leads Work Package 8, which is policy communication and dissemination. So as part of this, we're conducting a webinar series on all of the different work packages. Today is Work Package 5, 1 through 4, as well as 6. We went slightly out of order due to scheduling, are available on the SO-CHIC YouTube channel. I'll put a link to the SO-CHIC project in chat. So Work Package 5 is Impact on the Coupled Climate System, led by the University of Reading and Geomar Helmholtz Center for Ocean Research. We have the work package leader, David Ferreira, with us to introduce the work package and talk about some of the work that has been done so far, how it connects to the SO-CHIC project in general, and to answer any questions you may have. I would ask that you please ask questions towards the end of the presentation. Just use the chat box, I think should be fine. Dr. Ferreira is an assistant professor of meteorology at the University of Reading in the UK, where he specializes in climate dynamics, ocean circulation, and its interaction with the atmosphere and sea ice. Fun fact, I thought he also has a bit of a background in exobiology and exoplanet studies from his previous work at MIT. We're also privileged to be joined by Dr. Holly Ayres, a researcher on the SO-CHIC project and a postdoc at the University of Reading, specialized in Weddell Sea polymias. So with that, I'd like to invite Dr. Ferreira to begin.
Thank you. Thanks, Griffith. Welcome, everybody, for this webinar. Let me first share my slides. Hope you can see this.
Looks good.
Looks good? Okay, brilliant. So thank you for attending. So this webinar is going to be dedicated to Work Package 5, and this is so that in that team there are mainly 5 people involved in the work. Holly, who is just sitting next to me, is a postdoc with us here in Reading and has been working on the atmospheric response to the polynya, and she will be presenting some of that work in a minute. I am myself, David Ferreira, the work package leader, and then there's a group of people working on some other aspects, which we will discuss later, who are all sitting in Geomar. And Woonsoon Park, who used to be in Geomar and now moved to Korea, but is still tightly involved in the project. Okay, so briefly, the structure of the webinar. I will start by giving you a bit of context and background on the relationship between the atmosphere and the Weddell polynya, and even start by maybe reminding everybody what's a polynya. And then we will go through some of the ongoing work in the Work Package 5. That's going to be mainly 2 parts there. What we've been doing in Reading on the atmospheric response to the Weddell polynya, which has been led by Holly, and coupled interaction, so coupled ocean-atmosphere interaction between polynya and atmosphere, which is work in progress and led by Malin O'Dalan in GeoMar. And then we'll finish with some summary and perspective. Okay, so what is a polynya? If you're in SO-CHIC, you've probably heard that a million times, but let's assume that you're not necessarily in SO-CHIC or not even interested in general in the Southern Ocean. So a polynya is a large opening in the ice cover. So that's essentially a hole in the ice cover. So open ocean surrounded by sea ice. And there are many types of polynya. Here you have examples of open ocean polynya, so polynya which are away from the coast, but there are also coastal polynyas. Actually, you might see a tiny bit of that here in that photo here. There is a small hole near to the coast. But in this project, at least in this work package, we are mainly focusing on open ocean polynyas. And we are even more restrictive because we are interested in the Weddell Sea polynya. So the Weddell Sea is about here on this map. And we have two examples of very large polynya which happened, one in the 70s, 74 to 76. And in between, there were tiny little polynyas, but in 2016-17, a new polynya emerged again, almost 40 years later. That polynya in 2017, which is shown on the right here, was substantially smaller than the one in the 70s, sorry. But still, it represents a big hole in the ice cap, which we haven't seen for 40 years. Okay, so very briefly, some of the things we know about the polynya in a very rough way. When there is a polynya, what we expect is that there is a very intense air-sea flux within the polynya. We're going to come back to that later. Those air-sea flux are associated with deep ocean convection, which means that you have upwelling, so water which is rich, which is warm and rich in carbon and stored in the subsurface ocean is brought to the surface within the polynya. Some of the heat and carbon stored in that water is released to the atmosphere. And the deep convection and the loss of heat and carbon is potentially having an impact on the properties of the water masses inside the Weddell Sea gyre, and potentially having an impact that goes well beyond the Weddell Sea and on the global circulation. So to put this in the work of this package in the context of the SO-CHIC in general, our main concern here, it will be in work package 5, will be with the impact on the polynya on the atmosphere and on the climate in general. We have a strong link with the work package 4, which is looking at how the polynya appears and what are the conditions that appear before its formation, whether it is the preconditioning of the Weddell Sea polynya. And so some of that story in the work package 4 relates to what's happening in the atmosphere. We also have a tight relationship with work package 1, which is mostly focusing on air-sea interaction in the Weddell Sea gyre and more generally around the Antarctica. And as we will see in a minute, air-sea interaction is a key criteria. That's the starting point, effectively, of the work we have been doing in work package 5. Now we have also links to some of the other packages. For example, the change we are seeing in the heat being exchanged between ocean and atmosphere does enter into work package 6, where people are looking at how the polynya affects the heat and carbon storage in the atmosphere and in the ocean. And obviously, the change in storage in heat and carbon in the ocean is mainly due to the fact that it's going to the atmosphere. So there's a connection here. And similarly, the change in water mass properties that are associated with the intense air sea flux in the Polynya feed into the questions of work package 2 and 3, which look at the upper and deep change in water mass properties. Okay, so let's go back to something very simple. And why do we care? Why do we even wonder why the Polynya might have an effect on the atmosphere? And the idea is extremely simple, is that here you have a schematic that shows the surface of the ocean. You have the ocean below, the atmosphere above, and in between you have the sea ice. So in winter or late winter, typically when there is a sea ice on top of the ocean, the heat flux that goes from the ocean to the atmosphere is typically about 1 to 10 watt per meter square. It's a very small number. That's mainly because sea ice is a very good insulator. Heat diffuses very slowly within sea ice, and it's very difficult for the heat from the ocean to propagate through the ice into the atmosphere. When there is a hole in the sea ice, like the Polynya, but that's actually applying also to leads and cracks of various size, the atmosphere, which is very cold, typically minus 20, 30, will be brought in direct contact with the surface of the ocean, which is cold, but effectively is extremely warm compared to the atmosphere. So typically the ocean in those conditions would be minus 2 degrees Celsius. What it means is that the cold, dry air, which is flowing over the Polynya, is brought in contact with the warm and obviously moist ocean, which triggers a very strong air sea flux of sensible and latent heat. And so we know that in those Polynya, the air sea flux can jump from being 1 to 10 watt per meter square over sea ice to hundreds of watt per meter square in the Polynya. And so the expectation is that this massive perturbation to the system will change the state of the atmosphere. So there has been a bit of studies about the atmospheric response to the Polynya, and we have already some clues about what happens. The most obvious one is that all the heat which is released by the ocean into the atmosphere in the Polynya generates a lot of turbulent mixing in the boundary layer. So it's turbulent mixing which is driven by the buoyancy from the ocean. This means that, for example, we know that the boundary layer height, which may be a few hundred meters, is higher above the Polynya than it is above the sea ice. One of other consequence of this intense turbulent mixing in the Polynya is that the flow of air in the free troposphere, so well above the surface, is mixed downward to the surface much more efficiently in the Polynya than above the sea ice. And so a consequence of that is that the surface winds are often stronger above the Polynya than they are above the sea ice. And this has implications because it drives vertical motions. So on this side of the Polynya, you could expect, for example, downward motion and upward motion on this other side. And again, this has implications. We think that maybe there's a low pressure system developing over the Polynya, although that it's not as robust as we would hope for. We also know that there are significant changes in the cloud and the radiation. So the cloud cover increases above the Polynya. This changed how much short wave comes from the top of the atmosphere down to the surface of the ocean in the Polynya. And they also changed changes in the long-wave radiation. That said, there are many aspects that remain unclear. So some of those previous studies have been focusing on idealized cases. They've been using 2D models. And very often, and in some cases, they've used a very small sample to study the response of the atmosphere to the polymere. So we are still wondering about whether there is a three-dimensional response of the atmospheric circulation to the polymere. And if there is one, how local is it? Is it confined to the surface? Does it extend all the way through the troposphere, all the way to the tropopause? And does it extend horizontally away from the polymere by maybe propagation of waves? Now, if we think about the relationship between the polymere and the atmosphere, there is also a number of studies which have looked at the opposite direction. That is, the atmosphere is driving the polymere. And you can roughly separate those studies into two families. So there's a first family which has been invoking large-scale atmospheric circulation changes. And typically, they are linked to the southern annular mode. So the southern annular mode is the mode that describes the northward-southward shift of the jet stream. And so typically, those studies are making the point that change in the large-scale winds would drive increased upwelling in the Weddell Gyre, which would bring the warm water stored inside the ocean to the surface. And that would be helping the formation of the polymere by essentially melting the sea ice from below. There is another family of studies which are all fairly recent, which focus on the storminess. So by storminess, I mean how many storms, their intensity, the path of the storm, how changes in that storminess could influence the polymere. And there are various mechanisms by which storms could help the formation of the polymere. So if you have increased storminess, so more regular storms, you could generate more turbulent mixing in the upper part of the ocean. So upper part, I mean literally the 100 meters. And that turbulent mixing would bring the somewhat warm water which are stored inside the ocean to the surface and help melt the sea ice. And those storms can also push the sea ice around and create the hole by mechanically diverging the sea ice. There's been also some recent suggestions that atmospheric rivers, so very intense filaments of moisture which are embedded in the storms, could bring some intense surface warming and would also promote the sea ice melt. So here we are talking about more like a thermodynamical effects coming from directly from the atmosphere. And I would definitely recommend to look at work done in the work package 4, which has addressed some of those issues, and their webinar is also available on the SO-CHIC channel. Okay, so we've seen that the polymere could influence the atmosphere could influence the polymere, and so clearly we are dealing here with a two-way interaction between ocean and atmosphere when it comes to the polymere. So that brings the question of whether the polymere could be part of a coupled ocean-atmosphere mode of variability, where the feedbacks between ocean and atmosphere are sustaining a mode of variability that could have a significant impact on climate. It remains to be seen if such a mode were to exist, whether it would be local, maybe expanding over an hemisphere, maybe global. There have been a number of model simulations in the past, which have shown some global decadal variability, which is associated with change in the Southern Ocean deep convection and sea ice extent. So it's not exactly polynya, but it's in spirit, it's very similar to what the polynya does. And so those also are maybe supporting the idea that there could be such a mode of variability. Okay, so this brings us to the specifics objective of the work package 5. So one of our main goals is to investigate the atmospheric response to the Weddell Sea polynya. And by those, we mean literally to look at both the response of the full 3D atmosphere and to look at both the dynamical and thermodynamical response. So to get a full picture to build on previous studies. And then we'd like to quantify the effects of ocean atmosphere feedbacks on the polynya. So the atmosphere will respond to polynya. To which extent this response of the atmosphere is reinforcing or weakening the polynya? Does this interaction could help explain the lifetime of the polynya? And a key question that comes in there is that obviously, because we only have 2 examples of a Weddell Sea polynya in the last 40 years, we have to rely heavily on numerical modeling, climate modeling, to study the polynya. And this brings the question of how the polynya is represented in climate model. And as the field is moving toward higher and higher resolution in climate model, the question is whether the polynya dynamics is improved with a higher resolution. Okay, from there, I'm going to pass to Holly next to me. And so mainly discussing whether there is a 3D atmospheric response to the Weddell Sea polynya. And I need to change slides.
Yeah.
No. Oops. Yes, getting there.
Great. Tilt that so I'm less glitchy. Thank you very much, David, for a great introduction. I will just also minimize that. There we go. So I'm going to talk to you about our experiments with our atmospheric only models, so our AGCMs. First, I'll talk a little bit about our model setup. There we go. So yeah, the aim of this part of the project is to determine the atmospheric response to the Weddell Sea polynya, but also we're really interested in the differences between models and resolutions. So to do this, we use 3 atmosphere-only models and 2 sets of resolutions. So just in quick summary, we use HADGEM3, ECM5 and OpenIFS, and we use the highest and lowest resolution versions of those models. We ran 100 members or years for the low resolution, and for ECM5 and OpenIFS, we ran 30 years, and for HADGEM 15 because of computer budget resources. So you'll notice that the resolutions are very similar for HADGEM and for OpenIFS, about 100 kilometers in the low resolution, about 25 kilometers in the high resolution, but ECM5 is a little bit of an older model and has a much lower resolution for both of those versions. So bear that in mind. So what I'm going to talk to you about is the response to the polynya. So we ran 2 simulations for each of those setups. So that's a total of 12 simulations. And we ran an ERA 5 1974 polynya condition, so using sea ice concentration and sea surface temperatures for the 1974 polynya. And then we also ran a masked non-polynya control, so the same conditions but masked over the polynya with ERA 5, 1980 to 2015 data, so non-polynya years. So I'll be talking mostly about the response to the polynya, which is the difference between those two setups. And what we have is 100% ice loss, and as David has explained, that's about a 1 degree difference in sea surface temperature, and that's a big warming to the atmosphere, particularly in August, September, and October, which is when we generally find the polynya, kind of that late winter, early spring, when there's lots of sea ice around. So I'll just go through some of our results. So starting with the low resolution versions of the model for heat flux. So this is for HADGEM at the top here, August to November. And the stippling here is the statistical significance, student t-test 95%. And we have the same for ECM5 and OpenIFS. So the first thing you'll notice is the response is very locally confined, perhaps not surprising for heat flux, but it also decreases into November as the temperature gradient between the ocean and the atmosphere also reduces, and the polynya dissolves. So this goes from about 150 watts per meter to about 10 watts per meter squared in November. All very similar spatial pattern between the three models, but perhaps unsurprisingly, there are some differences in the magnitude. So HADGEM3 has a maximum of 147 watts per meter squared, ECM5 a much lower, 102 watts per meter squared, and OpenIFS, fairly similar to HADGEM, 131. So yes, as I mentioned, that's perhaps not unsurprising for any modelers. Different models do different things, but it definitely has piqued our interest, and I'll talk a little bit more about that in just a moment. So I'm just going to show you the first order response, so that direct response to the polynya for September-October means. And here we have the HADGEM3, ECM5, and OpenIFS means going across the page. We have near surface temperature here. And first of all, again, very much local, and spoiler for the results, everything is local. We don't get a big global response. It's all very much confined to the Weddell Sea. So there is a little bit of affection, but not really much. And then for sea level pressure, things start to get a little bit interesting. Generally, there's a negative response over the polynya. However, this isn't significant for all of the models. In fact, it's only significant in HADGEM. But you might notice that there's kind of a positive, an increase in the sea level pressure around the area, so perhaps some dependence on internal variability, so the polynya signal is comparatively smaller. So is that a response? Maybe. I don't think we really have a definite answer for that. Precipitation behaves a little bit nicer than sea level pressure, and it's highly localized, so there's not even any advection. The response is up and back down. So all very interesting results, and OpenIFS, interestingly, has slightly higher response than HADGEM. ECM5, unsurprisingly, has a much lower response, but all fairly similar and at least consistent. Just going on to the dynamic response, so at 850 hectopascals, which is just above the surface, we again have the September and October means here. So same layout as before. So here we have geopotential height, and things start to get a little bit messier. So we start to have less consistent results here. So what you'll notice here is that the significance is only present for OpenIFS, and that's only right in the middle of the polynya, just over here. We have an increase in HADGEM, but it's much smaller and it's not significant. And ECM5, we actually have a decrease. So we definitely can't say that this is a significant response to the polynya now. For zonal wind and meridional wind, again, we have a little bit more significance over in HADGEM and OpenIFS over here. And even in the meridional winds for ECM5 and OpenIFS, I still don't have HADGEM yet, but it's generally in geostrophic response with that geopotential height change there. So that's how the circulation kind of changes. So it's logical, it's consistent to the other variables, but whether or not it's actually a response to the polynya is another question. So then moving on to the zonal mean response aloft. So similar setup, but this is the zonal mean directly above the polynya. And again, hatching is significant, and the contours here are the climatology. So what you have, it's nice and clean for temperature. The temperature is very consistent between all three models, and there's this nice kind of warming bubble up to about 700 hectopascals. But interestingly, nothing really above that level. Then we have geopotential heights, and it's a little bit inconsistent, but I would say all of the models, even ECM5, kind of have this decrease at the surface, which makes sense with the sea level pressure, and then an increase above, up here. Maybe in different areas, but again, I'll go a little bit more into that in just a moment. Zonal wind, again, it looks messy to start with, but is it? I mean, if you think about it, the there's a decrease to the north in all of them and an increase to the south. So does this depend on something else going on in the model as to why we get a difference in the results? Perhaps. You'll notice in the climatologies, the maximum of the jet, so where the jet position is in a different location. So I'll go into a little bit more there in a minute, but that could be one factor as to why we're seeing different results. For the high resolution, so heat flux, very similar to what I showed before for HGEM3, ECM5, and OpenIFS, all August to November. You see, if you remember, it's very similar to what we have in the low resolution. So that's another thing, is that high resolution models don't necessarily mean that we're going to get a big global response. However, we do get an increase in the magnitude, not a huge one, but an increase that's piqued our interest. So we have a maximum increase of 45 watts per meter squared for HGEM, 38 for ECM, and OpenIFS has 33. So all very interesting. I won't go into all of the figures again, as I did for the low resolution, but here we have all of the models together, the mean over the polynya directly. So we have the heat flux, surface temperature, mean sea level pressure, precipitation, geopotential height, and zonal wind. HGEM in blue, ECM5 in red, and OpenIFS in yellow. And then the solid lines are the low resolution and the dashed lines are the high resolution. So if you look at heat flux, surface temperature, and precipitation, so this one here and this one here, it's all quite consistent between the models. Perhaps a slightly different response, but they're all at least the same sign. We can say the heat flux increases, the temperature increases, and even the precipitation, which is a little bit messier, still increases in those crucial months. Sea level pressure, so up here, mean sea level pressure, starts to show higher variability. So the signal becomes quite small, and as you can see, the zero line is here. So in most of the models, there is a decrease in sea level pressure, but by how much is very different. And even in some models, there are some years or members that actually go into the positive. So that's not a very consistent result. Geopotential height and zonal wind, a lot of variation down here. So again, let's use the same logic. Here's the zero line, and the results are all over the place, fluctuating either side. So I think we can say that there's definitely a lot of difference there. And I'll again go into a couple of theories about why that is, and how it could still be a response, but yeah, might not be. So we have, as I mentioned earlier, the jet. So the jet is just north of the polynya. And I'm going to just show a few comparisons between a couple of the variables and the position and the strength of the jet in the experiment. So the model response is the heat flux, geopotential, and zonal wind, and the jet is just for the experiment. So this is the heat flux against jet latitude and jet strength. and you've got your R² values up here. Blue is HadGem, yellow is ECM5, and green is OpenIFS. Same for geopotential height and the same for zonal wind. So there's a lot of information here. So I'm just going to very quickly summarize. So you have heat flux and geopotential height. For both of them, we have a weak correlation, but there is a correlation to jet strength, but very little to jet position, apart from in ECM5, which is actually on average a little bit further north. So potentially that could explain some of our results. For zonal wind, there has a weak correlation to jet position, but not jet strength. So the other way around. So the general idea is that with a more southward and strong jet would mean a bigger response. Is that true between the resolutions? So for HadGem3, so HadGem3 low resolution here, HadGem3 high resolution, blue is the jet latitude, the average jet latitude, and red is the average jet strength. So HadGem3 generally goes against this idea with a more southward and stronger jet in the low resolution, but the high resolution also has a lot less data, so that could be having a bit of an influence there. ECM5, the jet is further north, but is stronger in the low resolution. And OpenIFS is more consistent in jet position and jet strength, and has the most consistent response in all variables. So does this hold true? Yes, with very, very low confidence, but not without other factors coming in, and it depends on the variable that you're looking at. So just very quickly, a comparison to ERA5 reanalysis. So just to see if are the results realistic. So I've done the exact same thing using ERA5 1974 Plenia year. So that's only 1 year for the Plenia year. And also the mean of the 1980s, 2015. So I found the difference between those two. So exactly the same as the experiments, but because we only have that 1 Plenia year, there's a lot more going on. And yeah, generally, it seems to look pretty good, right? So if you remember our figures from before, the response to the signal is coming through, but if you look at our color bars, we also have a very similar magnitude for each of these. Even in sea level pressure, the background is negative, but we still kind of get the Plenia shape here. And for precipitation, this is a very clear precipitation response to the Plenia. So obviously only 1 year for the Plenia. We just wanted to have a quick check of the significance here. So we just did a normal distribution. So all of the 1974 means, which are the purple dots in each of these, so heat flux, temperature, sea level pressure, and precipitation, are statistically unlikely to occur naturally because they are outside of the curve. Precipitation and sea level pressure are within the normal distribution, so over here, but very much to the edge and are both at 2 sigma, so 2 standard deviations. So could this happen naturally? Yes, but it's very unlikely, especially with this kind of pattern. And yeah, I think that's my, thank you.
Okay, so I will now switch to another part of the work. Okay, so I will present the other main branch of the work in work package 5. So you should see now slides from Malin Odanan. So Malin and Joachim couldn't be here today, so I will present their work on their behalf. And if anything sounds strange, it's probably due to me rather than them. So I take responsibility for miscommunication here. So this part of the work being done in GeoMar has been done in part in collaboration with other people in Geomar, as well as collaborators of SO-CHIC in University of Gothenburg. So what Malin has been leading is the development of a couple model to study the polynya in the couple system. So the work that Holly was presenting is using just an atmospheric model in which we prescribe the sea surface temperature and sea ice conditions. But part of the work package is also to look into the coupled response. And so we want to have the two-way interaction between ocean, sea ice, and atmosphere to be able to see the feedbacks. So part of this work, this is ongoing work. So Malin started from a coupled climate model, which is called fossil one, and it's our standard configuration. It has an atmosphere, an ocean component, land, sea ice, and there is a coupler between all these components. Fairly standard climate model. You will notice that the resolution in the ocean is 0.5 degree. And what Malin has been doing is developing a version where the resolution in the ocean is increased significantly in the Weddell Sea region. So this is what it looks like. So taking this whole global model, Malin took a patch in the Weddell Sea region, so this orange dotted square there, in which the resolution was increased from 0.5 degree to 1/10 degree. And the intent here is that by increasing the resolution, we will increase the quality of the simulations and resolve some of the important physics that is not resolved in the 0.5 degree. So the 0.5 degree model still rely on eddy parametrization, while by switching to 1/10 degree, we hope to get a better resolution of mesoscale eddies and boundary currents. And from there, to be able to tackle some of the questions we are interested in with a higher fidelity tool. So the model is run with forcing from the 50s. So there is no climate change in that model at this point. And they have been the runs have been done for up to 100 or 200 or 250 years. So this is ongoing work, and at this point, it's about figuring out how the model works, really. So Malin has been looking at some of the key elements we are interested in. So for example, here, there is, in the lower right, there's a schematic of the Weddell Sea gyre, which is spinning around in a clockwise in the east of the peninsula. And the strength of that gyre has been estimated from observations. And so this is one of the indices that we would like the model to reproduce with accuracy. So as you can see in the model F1, which is the control without the refined nest in the Weddell Sea gyre, the gyre is already almost 100 Sverdrup. And when the nest is activated to have the higher resolution, you notice that the strength of the gyre jumps to 150, which is in both cases is above what we think is really happening in the observations. But there is also clear sign that increasing resolution does increase the strength of the gyre. If we look at another maybe key element that we would like to have right is to look at the strength of the Antarctic circumpolar current. And you can see that going from non-refined model to the refined model, there's a slight decrease in the strength of the ACC. And again, it's moving a bit away from observations. One of the reasons why we want to use this coupled model with a refined grid in the Weddell Sea is that we are interested in looking at the remote impact of the Paullinia outside of the Weddell Sea. And one of the hypotheses we are working with is the idea that maybe there is a change in the Atlantic overturning circulation in response to the Paullinia. And so one of the key things we are interested in is to make sure that the AMOC is properly represented in that model. So in the top panel, you have the overturning circulation in the North Atlantic from 30 south to 70 north. On the top, you have without the refinement, and in the middle with the refinement. And the bottom is the difference. So in both cases, the model reproduces very well the strength of the gyre at the rapid array around 26 north. So that's very encouraging. And as the resolution refined, you see that the strength of the overturning bottom cell gets a bit stronger and possibly a bit more realistic. So that's encouraging. So at this point, this is really ongoing work to develop the tools we need. And what has come out is some of the changes are somewhat expected, but not necessarily going the way we would like them to go. And so this needs further work. I will stop there for Malin's work. So development of a nested couple model, and go back to our presentation. So Holly presented her result, and I presented Malin's results ongoing at GeoMar. So now let's go to a summary of the results, and I will leave it to Holly.
Yep, so in summary of our results so far, particularly for the atmosphere model, so for the impact of the Paullinia on the atmosphere, our general result is a bit small, especially compared to natural variability in certain variables like sea level pressure and geopotential height, and it's very highly localized, so it's not this big global response. But that's still very interesting, and it's very robust across all three different AGCMs, and the available observations, of course, for ERA 5, although of course these observations are limited before the 1980s, and it's also consistent with the modeling experiments that have been done before. So what does this research mean? What are the implications? Generally, there's little to support remote or large-scale impacts or feedbacks to the ocean, and there's generally not much evidence of an existence of coupled mode of variability associated with the Paullinia. We are also obviously interested in potentially an ocean-atmosphere coupling, so atmosphere to ocean and then ocean to atmosphere again, to amplify the signal. Of course, this is something we wouldn't get in an AGCM, and we did use the largest Paullinia that we have in satellite record, and the idea of whether or not the ocean carries a signal to lower latitudes is still debated. So there's a lot of debate within this. We potentially have some missing processes or systematic model biases for these big result models. So again, high frequency variability in the Paullinia and shape. So potentially some are very large Paullinia or they occur a little bit too often. Finally, for the Plenia and atmosphere interaction, it's primarily a one-way interaction, right? So yeah, we have this kind of preconditioning and potentially some atmospheric processes and triggers. So yeah, what next? Final part of the project is to look at polynyas in Primavera datasets and SO-CHIC, so these large global climate models, and do a multi-model comparison. So our goal is to assess whether model resolution, both atmosphere and ocean, is important in a number of things. So the formation of the polynya, the ocean and atmospheric processes associated with the polynya, and the climate response to the polynya. But also, are there any robust responses or preconditioning for polynyas in models based on previous slide? So this is just an initial work on that. And this is by our master's student who recently finished, Carmen Wong. So this is using the Access ESM 1.5 model, which from previous work by Mormon et al., again, loosely related to SO-CHIC. This is the model in SO-CHIC that we see lots of polynyas, very high frequency, a little bit unrealistic again, but there's lots to go by here. And one very interesting result, for example, is this sea level pressure difference before the polynya occurs. So this is the difference between all of the polynya years and all of the non-polynya years in the model. So there's definitely something in the atmosphere happening before the polynya occurs. And so this is something we're interested in terms of preconditioning. Also potential relation to storms. And yeah. It's pretty significant with our HCM result as well for August, September, October. So all very promising stuff to go into next.
Okay. So we've reached the end of presenting our results and in general WP5. So I think we're happy to answer any questions. Do you want us to?
Yeah. Can you hear me?
Yeah, I can hear you. Yeah,
okay.
Yeah.
Good. Yeah, if anyone in the audience has any questions, please put them in the chat. But I can start out just with this is me doing my job as a policy officer here. Where did your data come from specifically? Do you know what sort of infrastructure and instrumentation was used to gather the data that you were using?
You mean for the polynya?
Yeah.
So that was ERA 5 data, right? So that's reanalysis data, which is observation data, mostly satellite remote sensing, especially for before the 1980s when we have so few observations in general. And then it goes into these models, which are reanalysis models to basically give you lots of grid points and interpolate the data. So it's not perfect, but it is all we have for before the 1980s.
Yeah.
Yeah.
Thank you.
Thanks.
I'll give it another one. So you were talking about how the effects of polynya are mostly local. They're sort of small scale is what you've been finding, if I'm hearing that correctly. So we're sitting here in Europe, an ocean away, quite literally, and we're studying polynyas. And when you're a policymaker, if you're in DG Mare or an environmental ministry, and you look at this, how do these results translate into sort of European decision making or priorities on the climate or the ocean?
Yeah. Okay. Yeah. So when we started the project, there was a number of hypotheses that linked global climate to the polynya. And one of the most obvious was that when you open the polynya, there's a lot of heat and carbon which is released into the atmosphere. And potentially of that heat and carbon can be transported all over the globe. And so we know that the Southern Ocean is the place where most heat and most carbon goes into the ocean, effectively slowing down the rate of global warming. So there's a particular concern with how the Southern Ocean moves, reacts, changes. It's like a buffer. And so we want the buffer to keep buffering, essentially, to put it shortly. And so we definitely know that the polynya is opening a big hole in the buffer, if you wish.
Right. So
it's not very scientific terms there, but so one hypothesis was also that leak would change the atmospheric circulation. What we are finding is that it doesn't. So maybe in a way it's a good news. However, there is still carbon being released by the presence of the polynya, which is not this, which is more WP6. But for what WP5 is concerned, there isn't that big response we care that will propagate all the way to Europe in the atmosphere.
Yes.
Yeah, the ocean part is being solved by what people in GeoMA are doing. So at least we know that there is not a propagation of something in the atmosphere to Europe.
Okay. So this is sort of, yeah, solving one hypothesis by saying that this is maybe not a major source.
Yeah.
Okay.
Yeah.
If we flip that, your model was suggesting also that there could be many more polynyas in the future from atmospheric triggers. Is that, did I hear that correctly?
So there is one quite famous paper that actually it's a collaborator of SO-CHIC, Casimir Delavergne, who is in Paris, who wrote this paper a few years back, maybe 6-7 years back, I can't remember, maybe more than that. 9 years. Okay, yeah. Who was looking at the frequency of polynya in climate simulations for future climates. What he found is that there were less and less polynyas. However, okay. Yeah, just that because of the storminess ID, the change in storminess could be a trigger in the emergence of the polynya. People are a bit rethinking this idea that maybe if we go to a future climate, this is more the storminess that matters, and whether that was properly represented in the models we were looking at the time of that Delavergne paper. So people are rethinking again. I can't give you an answer whether there are going to be more or less. That's okay. What I'm of.
This is maybe a future research topic to revisit that theory.
Yeah.
Good. We don't have any questions yet from the audience, but I want to give people a few more minutes to ask if they still have any. So where I was going with the last question is that if the impact of a polynya is so local, does it have any major environmental impacts on the local area? If it doesn't have such a global impact, would you say that there are major environmental implications in the specific region?
No, because well, it's so localized that it would really only concern people who live there, which is pretty.
It's not so many.
Which is pretty short.
It's quite far from the coast.
Yeah. One starting hypothesis was that the polynya would change the EMOC, and we know from totally different literature and direction of research that the MO change can have a big impact on the location of the what's called the ITCZ, intertropical convergence zone, which is the rain, that's the rain belt around the equator. So we know that changes in the MMOC can change the location and intensity of that belt. And obviously, as soon as you touch the ITCZ, you're talking about billions of people and the water resources and monsoon. If there is such a link, it's not through the atmosphere, it will go through the ocean. And that's the type of question that Malin will be addressing.
All right. Well, thank you for the responses. I'll just ask one last thing. How have you interacted with the other SO-CHIC work packages just to try and bring this all together? Have you guys had any impact on your work based on what the other work packages have been doing?
We've mostly interacted with WP4 because effectively they are looking at the other side of the coin.
Right.
They're starting from the ocean and what are the preconditions that are necessary to get the polynya. And I think that they start in mostly thinking about ocean, but it's really you know what they are finding is that the atmosphere actually seems to be a key element to get the right trigger. So you still need the ocean to bring all that warm water rich in carbon in the subsurface of the Weddell gyre. But the triggering mechanism seems to be really related to atmospheric events. And I think if you combine what they're finding with what Holly has been finding, is that we are seeing this one-way interaction where ocean and atmosphere set up the stage, and then the atmosphere gives you the kick to open the door. And that's probably where we are going to be going with the future work, mostly on this one-way interaction, and try to bring then at that point the two views of the two packages together.
Good. Well, I want to thank you very much for your presentations again and all of the work that you've done. There's far too much for me to attempt to summarize, but there's been a lot of good work happening, and you've got more than another year of work ahead of you, if I'm not mistaken.
Yeah.
Yeah. So let me just conclude quickly by saying that the recording of this webinar will again be available on the SO-CHIC YouTube channel. We're still setting the dates for Work Package 7's webinar, but we're hoping for March, and there will also be a SO-CHIC policy briefing happening likely in May. So thanks again to everyone who attended and to our presenters, and I'll let it go there. So thanks very much, everyone.
Thanks everyone. Bye.
Bye.
Have a good afternoon.